In this final section of Chapter 1, we complete looking at the requirements, requirement 4 of estimating internal values of power and energy and so forth. And we also look briefly at some of the state of health diagnostic kind of information of requirement 5. We begin by thinking about energy versus power, and we're going to start at the cell level, not at the pack level. So cell total energy versus cell power. And this graphic may be helpful to you. I thought it was kind of fun and helpful to me in thinking about energy versus power. It's the Slurpee versus the straw, if you will, and energy is the Slurpee and power is the straw. Energy is the ability to do work. It's a total quantity. We measure it in watt hours or kilowatt hours. Power is not the total amount, but the rate at which I can use energy. It's the rate at which energy can be moved from the battery pack to the load or vice versa without exceeding some design limit, such as a voltage limit or an electronics limit. Power is an instantaneous quantity. It's not work can extend over a long period of time, but power is right now. Power equals current times voltage, and it's measured in watts or in kilowatts. Discharging or charging at too high a power level is going to accelerate cell degradation, and it leads to your battery pack failing prematurely, and that's really the main limiting factor when we're calculating how much power is available. We, generally speaking, will calculate cell power to enforce design limits. And these could be on cell voltage or on cell current. And an important feature of the power estimates that we have to provide to the vehicle or to the load is that they are predictive. We don't say this is how much power you could have this microsecond, and by the way, next microsecond might be different. We say this is how much power you can use constantly over the next delta t seconds into the future, where delta t might be something like 10 seconds. And then you update your prediction that you deliver to the vehicle at a much faster rate than once every delta t seconds. So this is often on the order of 10 seconds, somewhere around there. We update at a rate, this is often on the rate of 10 to 100 hertz is common. I don't think it has to be done that quickly, but that's commonly done. So I'm predicting for this long period, and then I'm updating my prediction overlap and so forth. And the idea of updating so quickly is even if my prediction was wrong, I get a chance to correct it before it's actually acted on. But the prediction should be relatively accurate so the vehicle can make long-term decisions of, do I need to spin up the engine to get more power out of the engine versus taking power out of the battery pack, and so forth. We're going to look in Chapter 6 at some advanced methods to compute cell power, and at Chapter 7 even more researchy, futuristic ways of computing pack power in an even better way. In the meantime, I would like to at least talk about how cell power could be computed with a fairly simple way, and this is actually what most vehicles implement right now. So it's simple and it's commonly used. Not the best thing to do, but it does okay. What we do is we take a battery cell at some state of charge, so some rest voltage, and in this case I ran a cell test in the laboratory, and I rested for 10 seconds, and then I discharged for 10 seconds, and I rested for 10, and I charged for 10, and I rested for 10. We did this kind of thing in simulation a lot last semester, so you should be familiar with this. The delta t here is the prediction interval for my power computation. So that's not, 10 seconds wasn't randomly chosen, it's whatever delta t is for your application. So if you have an application that requires a delta t of 5 seconds or 15 seconds, whatever, you run the tests that long. And what we're interested in is how much does the voltage change total over those delta t seconds. So it's not the instant drop, which would bring me down to here, but it's the total drop, which brings me down to there. So the delta V dis is the total voltage drop, which includes this drop. We know from our equivalent circuit models that would be like the R0, but it also includes some change in voltage due to the SOC changing and the open circuit voltage changing, and also due to concentration gradients building up and stuff like that. We then compute the discharge resistance for a delta t second discharge as this delta V dis over I dis. Do the same thing over here for charging. I charge for delta t seconds, in this case 10 seconds. I measured the delta V charge, it's the total change in voltage between there and there. And I calculate a charge resistance as well. So the charge resistance is more than just R0. Discharge resistance is more than R0. It also takes into consideration somewhat the voltage change over that interval due to other internal effects of the cell. Then, in order to use that data to produce estimates of how much power is available, we assume a very simple equivalent circuit cell model. And you can go back to last semester and realize this was just about the simplest one we ever looked at. So there's no hysteresis in the model, there's no diffusion voltages in the model, it's simply open circuit voltage and a resistor. So the measured, or the terminal voltage in this model, is open circuit voltage as a function of state of charge minus the cell current times the resistance, R. And I can solve that for I by rearranging, so bringing voltage over there and the dividing by R, and I get I is OCV minus V divided by R. To compute a power estimate, we're going to assume that the design limit that I can't exceed is a terminal voltage limit, and I have to keep the terminal voltage between Vmin and Vmax at all times. So for discharge power, we are going to use this expression for current. We're going to say power discharge equals the voltage, terminal voltage of the cell times the current. And the terminal voltage, we're going to put that at its limit. It's going to be Vmin. We're going to force it to Vmin to get the maximum discharge power out that we can. And Vmin is the voltage, and then this here is current, so it's right here, OCV minus V over R, where V is equal to Vmin, and that is our discharge power computation. Do we know everything? Yes. Vmin here is a design variable, it's a constant, we know it. We measured this from that lab test up there. We presumably know the present state of charge and the open circuit voltage thereof. So I can compute discharge power using this equation, and if my cell model is accurate, which it isn't quite, but if my cell model is accurate, then we can use that power for delta t seconds and we will not exceed a voltage limit. For charge power, we do basically the same thing. Power equals voltage times current, except now I'm using Vmax instead of Vmin, and I'm using the charge resistance instead of the discharge resistance. Vmax is bigger than OCV, so we're going to have negative power for charge, which is fine, except that in my experience, most OEMs require power to be delivered as a positive number, so we just multiply by -1, or we rearrange the computation to have the -1 in it, so it's Vmax times Vmax minus OCV. Notice that this got switched around. This calculation of power is very crude. It used a very simple cell model. It assumed that the cell was in an equilibrium condition at the beginning, and a bit more subtle, it assumed that voltage limits are the right thing to try to enforce. We'll see in Chapter 6 that there are better ways of computing power that use a full cell model, and we'll see in Chapter 7 that voltage limits are probably not the right thing to enforce, and some ideas of what might be the right thing to enforce. In any case, this estimate of power is usually a little bit aggressive, and so we multiply by some factor less than 1 like maybe 80% or 90%, to back off a little bit from the computation to have a safety margin in the value of power that we report to the vehicle. Cell total energy. So that was power, this is energy. And energy is power integrated over time, if you will. So the units are volts times amps times time, or volts times amp hours. Oh, wait a minute, amp hours or amp seconds, I know about those. That's the capacity. So the total capacity of this cell, multiplying a voltage of a cell as it traverses from its present voltage down to its minimum allowed voltage, gives me the maximum energy that I could ever get out of this cell. It's a weird integral. I'm not integrating with respect to time. I'm actually integrating with respect to state of charge. In this graph, I show open circuit voltage relationships for a number of different cells. Suppose we try to take the red one on the top. I'm presently at 50% SOC, and I'm allowed to operate down to 10% SOC. So the voltages that would go into this integral are all of the voltages from 50% down to 10%, and I would get some result for energy. Now, this integral is not something you would want to do in real time, and you don't have to do it in real time because open circuit voltage doesn't really change in a cell. You know, if you factor in degradation, it will a little bit over time, but it's actually pretty stable. So open circuit voltage, I can integrate in my table from Z-min to any desired Z and of open circuit voltage, and have a table lookup of this function, and it will look something like this. So if this is Z-min, I would have this integral OCV right over here, and it's 0. Oh, darn. It's 0 up to Z-min because I don't allow operation below Z-min, and it's not quite linear, but it's actually surprisingly close to linear looking, integrating open circuit voltage from Z-min up to Z-max, whatever it is. So in the application to compute energy of a cell, a single cell, remember, I would look up what is the state of charge of the cell. We'll learn how to do that chapter 3. There it is, and I go up here and I go over here, and that is the value of the integral. I just stored it in a table and I looked it up. I multiply it by Q and I'm done. There's my energy. Or if you want to cheat a little bit, you could say the nominal voltage of this cell is somewhere in between, so it's approximately Q times V nom times whatever state of charge range you're using. You're just assuming that the voltage is constant to do that. And that's not quite as accurate, but this is what's commonly used if people are referring to the energy capacity of a lithium-ion cell. They would just take the nominal capacity, the nominal voltage, and the range of SOC that's used. Total energy is not a function of rate being the current pulled from the cell, and that is something that really disturbs people. The energy that I get out of a cell may be a function of rate before I hit a voltage limit, but the energy is still there. I just have to get it out at a slower rate. So the total energy is really how much energy can I get out at an infinitesimally small rate. If I just kind of very, very slowly pull energy out, what is the maximum amount that I can get out? And we would have to perform a more complicated equation to say, well, what is the energy that I can get out at a 1C rate before hitting a voltage limit? We could figure out how to do that, but that's really, practically speaking, not important. The rate confusion of how much energy can I get out at a certain rate is really asking the question, how much power can I get out without hitting a limit? And that's why we need the power estimates as well. I say that total energy is not a function of temperature. Well, that's almost true. Open circuit voltage is a function of temperature, but as we saw last semester, the open circuit voltage of a cell might change only on the order of maybe a half a millivolt or something like that per degree Celsius. So it's a very, very weak function of temperature. Yeah, as I heat the cell up, maybe there's more energy available, or as I cool it off, there's maybe less energy available. But that's not really what people are thinking about when they're thinking about cold temperatures. At cold temperatures, they're thinking, wow, the cell is such a high resistance because of the temperature that I can't get any power out without hitting a voltage limit. Therefore, it appears to me that I've got less energy. I don't have less energy, I just can't get it out until I heat up the battery cell. It's still there, didn't go anywhere, but I can't get it out until it warms up a bit. So these are some tricky things, and it makes it actually pretty complicated to decide what to tell the user. What do you put on the dashboard of your electric vehicle? If it's really cold out, but my vehicle battery pack is completely full, maybe I really can't drive that far before I hit a voltage limit because of the high resistance, because of the cold temperature, so it looks like I've got less energy. So maybe I should maybe I should change the gauge on the dashboard to reflect the cold temperature. But then that's really weird because as I'm driving and the battery pack is self-heating, all of a sudden it looks like I've got more energy. Where did it come from? Well, it didn't come from anywhere. It was already there. But what should I do with that? So designing dashboard gauges is a very, very tricky exercise because it involves not only engineering but also psychology of how do people interpret these gauges and how do you want them to interpret it? Can you teach them to interpret them differently from the gas tank on their car, which always went down, it never went up, and so forth. So when I'm working with clients, I prefer to give them only the total energy and have them figure out what to do with it, how to display that on the gauge. And usually they're much better suited for that exercise than I am. That was all computing cell level energy and power. Now we're looking at the pack level. I put a bunch of cells together and make a battery pack. Well, how much energy is there and how much power is there? To compute pack power, it's actually not that hard. If I know the power available from all of the cells in the battery pack, I just look for the lowest one of those and I multiply that value by the number of cells in the battery pack. And if I use that much power, the lowest cell will hit its limit, but none of the others will. So I won't exceed a design limit on any of the cells, but we recognize that there's energy in the pack that I can't get out because of some imbalance of some property. So again, Chapter 5 on balancing is important. To compute pack energy, you have to do a thought experiment. And what you do is you start with your pack in whatever configuration it presently exists at. So here I've got a cell charged at 100% and another cell, maybe it's at 80%, something like that. And I do a thought experiment. I don't actually discharge the cells. That would take time and it would be silly. I'd be wasting energy. But I in my mind, in my algorithm, I discharge the cells all the way down to the minimum state of charge. And because each cell might have a different capacity, that's not necessarily a straightforward calculation. I can't just do it once. I have to do it for every cell. So how many amp hours have to be removed to go from 100% down to, from probably 80%. This cell is probably going to hit the limit first. How many amp hours do I take out of each cell before I hit its limit? Then I take the minimum number of amp hours. The minimum number of amp hours would bring this one to Z-min. This one would not get to Z-min. I'm getting a certain number of amp hours out here. It would get to Z-low, but it wouldn't get to Z-min. Okay, so I figure out the number of amp hours that discharges the lowest cell to Z-min, and then I compute what are the final states of charge for all of the cells in the battery pack. So I know the initial state of charge, I know the final state of charge for every cell in the pack. And then the pack energy is simply the sum of the energies delivered by each cell. So it's the sum of the capacity of each cell. The cell capacities may be different. The operational ranges of each cell, I go from Z low to the present Z, of the OCV curve. So this again can be done with table lookup. In this case, it would require two lookups. I have to look up the OCV at Z and the OCV at Z low integrated and then subtract the two. But that can be done. It can be multiplied by Q, and I've got a fairly efficient way of computing total pack energy. And that's actually our final energy calculation. We never improve on that. That's the correct thing to do, and we're done. We do show how to do power differently later on. Before we end, just a few words on diagnostics. And a battery management system is usually required to report something called state of health, or SOH. And we also had to report state of charge. We saw that earlier. State of charge is something physical. I could go all the way down to the electrochemical level and tell you what state of charge meant. But state of health is something that I can't really tell you. It's kind of a vague term. But whenever you're building a battery management system, you have to make a requirement for what it means. And usually what it means is that people want to know some quantification of cell age. And there's two indicators of cell age that are usually used. One is the present capacity of the cell, and one is the resistance of the cell. And the capacity of a cell will decrease between 20 to 30% over life, and that's called capacity fade. The resistance increases between 50 and 100% over life. That's known as power fade. Notice that at so-called end of life, EOL, of a battery pack, I still have at least 70% capacity left, and I still have the ability to pull quite a bit of power out, about half the power I could before. So by no means is the battery pack dead when I consider it end of life. There's still a lot of possible life in it. It's just that maybe it doesn't perform well enough to be used in its primary application any longer. Maybe I need a second life application like stationary storage for a solar array for a house or something like that. But it's not like a 0-1 thing where it was working yesterday and now it's dead. Nope, it's quite different from that. If we estimate resistance and capacity as the pack operates, that will give indicators of life, and we study that in Chapter 4. Spend quite a bit of time on that there. People also for diagnostics are sometimes interested in state of life. State of health tells me about the present. It tells me what is the resistance right now, what is the capacity right now. I can compare that to the original and say how much capacity was lost or how much resistance was gained, and so forth. But state of life is a different idea which tries to predict how much life remains. It's a predictive quantity, maybe as a percentage or maybe as a calendar saying, oh, you've got 3 years left on this battery pack, or you've got something like that. That's much harder to produce a good estimate of. The issue is that future rate of cell abuse may not be the same as the past rate of cell abuse. Aging may accelerate or decelerate. You may move from a nice temperate climate to Phoenix and park it on asphalt all the time, where you've got amazingly hot temperatures and your battery pack just rapidly deteriorates. There's no way of knowing what the user is going to do in the future. So state of life is something that is a pretty tricky idea, and I think that's best left to the OEMs to come up with their own proprietary ways of doing that. And I'd be much happier trying to estimate physical quantities like resistance and capacity instead, and letting them use those physical quantities as inputs. So that's my premise. It's more useful to know the state of the internal physical degradation mechanisms, because how the degradation is happening is actually critical too, instead of only resistance and capacity. We talk a little bit about this, not in 7.8. There is no 8 in Chapter 7. Again, if I ever develop a third course in the sequence, as I'd like to do someday, the third course will use physics-based models for battery management. We'll get into some of these deeper thoughts of how does physical degradation happen, how should that impact my power calculations, how should that impact my life predictions and things like that. That's a follow-on idea. That's a pretty advanced idea. brings us to the end of chapter 1. And as a roadmap of where we're going from here, we're going to focus on estimating battery internal state and how to control the battery operation for some kind of an optimal trade-off between life and performance. We're going to use equivalent circuit models of batteries almost exclusively this course, but I believe in the future, ultimately, the physics-based models will give us better results. But the same ideas will apply. So we have to understand how batteries work to do anything more in this course. So we're going to review the battery modeling again, specifically the equivalent circuit models, and remember how to simulate them, how to think about them in terms of not just single cells anymore, but now multi-cell battery packs, and how that changes the simulation idea and paradigm. And that's the focus of the next chapter. And then after that, we look at estimating state of charge and estimating resistances and capacities and power and so forth to really focus on the estimation requirements of the battery management system and the diagnostics. Before finishing this chapter, I want to do due diligence here and let you know that I'm walking a pretty fine line teaching this course. Many or most of the methods that we talk about in this course are patented and owned by EV-related companies. And there's a very, very rich set of patent literature on the kind of things that we talk about. So I have to say something that's kind of a little bit weak, like I'm teaching you this for educational purposes only. That's not entirely true, but you do have to be careful in what you do take from this course. And what I hope you take from this course is not a set of recipes or cookbook procedures for how to implement these algorithms, because those are patented and that's not going to work for you. But I want you to understand how to think about the problems that these algorithms are attempting to solve, because they may or may not be the best way of doing it. There may be other ways of doing things that people haven't even thought of that will be better for you to use in your application. So please get below the surface. Please go deeper. Please think about these concepts and understand them, and not just try to get the minimum out, but try to get the maximum out of this course. So you could say, well, Platt, why did you choose those algorithms? Why didn't you choose something else that's in the public domain in the literature? Well, frankly, almost everything in the literature is also patented and owned by EV-related companies. They just patent it first and then they publish it. So the companies have developed these things for their own use, and they use them and they publish them for the broader community to see. But don't be too discouraged. There's a huge opportunity here of researching and developing methods that are sufficiently different from those that we talk about, so that one, you can implement them freely or distribute them freely and put them in open source if you want to, or that you may patent them if you want and own the rights to them. I think this is particularly true in moving. You need to understand this course before you can move beyond this course. You need to understand the equivalent circuit-based methods before you can go on and look at the electrochemical-based methods. But frankly, I think the equivalent circuit methods are going to be okay in industry for maybe the next 5 or 10 years. But my personal conviction is that it's going to go to physics-based models within 5 to 10 years from now. And there's much less patented material out there for those. So there's a big opportunity to look for more advanced methods than those that are presently available that solve different problems and do even better battery management. So yes, take this for educational value. No, don't implement everything exactly as you see it in a real product, but instead use this as inspiration to develop something even better. All right, so with that caveat, we finished chapter 1 and we move to chapter 2, and we review some battery models and learn how to simulate battery packs.